Freeman Dyson's role as a bridge between rival quantum theories is one of the most important yet often underappreciated achievements in modern physics. At a time when quantum mechanics was already successful but deeply fragmented, Dyson provided something the field desperately needed: unity, clarity, and communication. His contribution did not come from inventing an entirely new theory, but from recognizing that several brilliant physicists were, in fact, describing the same physical reality in different and seemingly incompatible ways. By connecting these approaches, Dyson transformed quantum field theory from a confusing collection of rival methods into a coherent and powerful framework. In the years following World War II, physics entered a revolutionary phase. Quantum electrodynamics (QED), the theory describing how light and matter interact, was producing astonishingly accurate predictions. However, the theory was also plagued by serious mathematical problems. Calculations often led to infinite results, which made no physical sense. Even worse, the scientists working on QED were divided into camps. Richard Feynman used intuitive diagrams and path integrals. Julian Schwinger relied on highly formal and abstract mathematics, and Shinichiro Tominaga developed yet another formulation based on relativistic quantum mechanics. Each approach worked, but they looked so different that many physicists believed they were fundamentally incompatible. This situation created intellectual rivalry and confusion. Physicists trained in one method often could not understand the others. Feynman's diagram-based approach, for example, appeared almost suspiciously simple to those accustomed to Schwinger's dense equations. Meanwhile, Schwinger's work seemed overly complex and inaccessible to those inspired by Feynman's physical intuition. The field risked becoming divided not by experimental disagreement, but by language and style. It was into this fractured landscape that Freeman Dyson stepped. Dyson was uniquely suited to act as a bridge. Unlike many of his contemporaries, he did not strongly identify with a single school of thought. He had a broad mathematical education, deep physical intuition, and an exceptional ability to understand different perspectives. Importantly, Dyson was not emotionally invested in proving one approach superior to the others. His goal was understanding. When he carefully studied the work of Feynman, Schwinger, and Tominaga, he realized something remarkable. Despite their different appearances, all three formulations of QED produced the same results and were mathematically equivalent. Dyson's insight was revolutionary because it shifted the debate from competition to unification. He demonstrated that Feynman diagrams were not an alternative theory, but a powerful computational tool that emerged naturally from the same equations Schwinger used. Dyson showed how Feynman's intuitive pictures could be translated into precise mathematical expressions, making them rigorous and acceptable to more formal physicists. At the same time, he revealed how Schwinger's abstract equations could be interpreted in terms of physical processes represented by Feynman diagrams. One of Dyson's most influential achievements was organizing QED into a systematic framework. He introduced clear rules for using Feynman diagrams, explaining how each diagram corresponded to a specific mathematical term in a perturbation expansion. This made calculations more manageable and transparent. Instead of wrestling with endless equations, physicists could now visualize particle interactions and compute results step by step. Dyson did not invent Feynman diagrams, but without his work, they might have remained a curious but controversial idea rather than a standard tool of physics. By proving the equivalence of the rival approaches, Dyson also helped resolve the crisis of infinities in quantum field theory. Renormalization, the process used to eliminate infinite results and extract meaningful physical predictions, became widely accepted partly because Dyson clarified its logical structure. He showed that renormalization was not a mathematical trick, but a consistent and reliable method grounded in the theory itself. This restored confidence in quantum field theory and allowed it to develop further. Dyson's role as a bridge went beyond mathematics. He also served as a communicator between personalities and cultures within physics. Feynman, Schwinger, and Tominaga had very different temperaments, working styles, and philosophical attitudes toward science. Dyson understood all of them and could explain each one's ideas to the others. In doing so, he reduced misunderstandings and helped build a shared intellectual community. His work demonstrated that scientific progress depends not only on new ideas, but also on translation and interpretation. Another remarkable aspect of Dyson's bridging role is that he achieved all this without ever earning a PhD. This fact highlights an important lesson about science. Transformative contributions do not always come from traditional paths or formal credentials. Dyson's strength lay in synthesis rather than specialization. He excelled at seeing the big picture and recognizing connections that others missed. In a field increasingly driven by narrow expertise, his approach was both rare and invaluable. The long-term impact of Dyson's unifying work is difficult to overstate. Modern particle physics, including the development of the Standard Model, relies heavily on the methods he helped formalize. Quantum field theory is now taught as a unified discipline, with Feynman diagrams as a central tool and renormalization as a standard procedure. The rival camps of the 1940s no longer exist, largely because Dyson showed they were never truly rivals at all. Freeman Dyson's role as a bridge between rival quantum theories teaches a powerful lesson about the nature of scientific progress. Breakthroughs do not always come from bold new inventions. Sometimes they come from understanding, connecting, and clarifying what already exists. By uniting competing formulations of quantum electrodynamics, Dyson gave physicists a common language and a shared foundation. In doing so, he did not just solve a technical problem. He changed the way physics itself moves forward. Freeman Dyson unified different formulations of quantum electrodynamics by doing something rare in the history of science. He showed that apparent disagreement was actually hidden agreement. In the late 1940s, quantum electrodynamics, the theory describing how light interacts with charged particles, was producing some of the most precise predictions ever made in physics. Yet at the same time, it appeared deeply divided. Several leading physicists had developed successful but radically different mathematical approaches to the same problem, and many believed these approaches were competing theories. Dyson's achievement was to reveal that they were not rivals at all, but complementary descriptions of a single, consistent framework. At the heart of the problem was the complexity of quantum field theory itself. QED combined quantum mechanics with special relativity, creating equations that were powerful but notoriously difficult to handle. Calculations often produced infinities, and different researchers tackled these problems in very different ways. Julian Schwinger developed a highly formal and mathematically rigorous method based on operator techniques and Green's functions. His approach was admired for its precision, but criticized for being almost unreadable to anyone not trained at the highest mathematical level. Richard Feynman, by contrast, introduced a more intuitive method using spacetime pictures of particle interactions, later known as Feynman diagrams. Shinichiro Tominaga independently created a relativistically consistent formulation using different mathematical tools. All three approaches worked, but they seemed so different that many physicists doubted they described the same underlying theory. Dyson entered this debate as a young physicist with a rare combination of skills. He was mathematically sophisticated, but he also deeply valued physical intuition. More importantly, he was willing to study all three approaches without bias, instead of asking which formulation was correct. Dyson asked a more fundamental question: what do these theories actually have in common? By carefully comparing their predictions and mathematical structures, he discovered that they were, in fact, equivalent. They produced the same measurable results and were built on the same physical assumptions, even though they used different languages to express them. One of Dyson's key insights was recognizing the role of perturbation theory in all formulations of QED. Each approach calculated physical quantities as a series of small corrections, expanding around a simpler problem. Dyson showed that Feynman's diagrams were not an alternative theory, but a visual and organizational way of representing the same perturbation expansion found in Schwinger's equations. Each diagram corresponded to a specific mathematical term, and the rules for drawing and interpreting diagrams could be derived directly from the underlying equations of quantum field theory. By making this connection explicit, Dyson gave Feynman's method mathematical legitimacy. Before Dyson's work, many physicists viewed Feynman diagrams as clever but informal tricks. Dyson demonstrated that they followed precise rules and could be systematically applied to compute physical processes. At the same time, he translated Schwinger's abstract formalism into more intuitive physical terms, showing how complex equations described concrete interactions between particles. This two-way translation was essential to unification. Another crucial aspect of Dyson's work was his clarification of renormalization. Infinities had long haunted quantum electrodynamics, threatening to undermine its credibility. Different formulations handled these infinities in different ways, which made the theory seem inconsistent. Dyson showed that renormalization was a universal procedure across all formulations. He explained how infinite quantities could be absorbed into a small number of measurable physical parameters, such as charge and mass, in a consistent and predictive way. This helped establish renormalization as a legitimate and necessary part of quantum field theory rather than an ad hoc fix. Dyson also introduced a clearer organizational structure to QED calculations. He explained how to systematically classify interaction terms by order, making it possible to decide which contributions were most important for a given level of precision. This made the theory more practical and accessible. Physicists could now agree not only on the final results, but also on the method used to reach them. This shared methodology was a key step in unifying the field. Beyond the technical details, Dyson's unification had a profound cultural impact on physics. By showing that Schwinger, Feynman, and Tominaga were all working within the same theoretical framework, he reduced rivalry and misunderstanding. Physicists trained in different traditions could now communicate more effectively, using a common set of concepts and tools. This helped turn quantum electrodynamics into a standard, teachable theory rather than a collection of competing schools. Dyson's work also demonstrated the importance of synthesis in science. He did not invent QED, nor did he introduce a radically new formalism. Instead, he clarified, organized, and unified what others had already created. This kind of contribution is often less visible than dramatic discoveries, but it is just as essential. Without Dyson's unification, quantum electrodynamics might have remained fragmented, slowing progress in particle physics for decades. The long-term consequences of Dyson's achievement are evident throughout modern physics. The techniques he helped formalize became the foundation of quantum field theory as a whole, influencing the development of the Standard Model and countless applications in particle and condensed matter physics. Today, physicists take for granted that different formulations of a theory can be equivalent, but this understanding owes much to Dyson's work. In unifying the different formulations of quantum electrodynamics, Freeman Dyson changed the trajectory of theoretical physics. He showed that clarity, communication, and conceptual unity are as important as innovation. By revealing the deep connections beneath surface differences, Dyson transformed QED into a coherent and enduring theory, securing its place as one of the greatest achievements of modern science. The importance of mathematical clarity in modern physics cannot be overstated, because mathematics is not merely a tool used by physicists. It is the very language in which the laws of nature are written. Modern physics deals with phenomena far beyond direct human experience, such as subatomic particles, curved spacetime, and quantum fields. In these domains, intuition alone is insufficient. Only clear and precise mathematics allows physicists to describe reality accurately, test ideas logically, and communicate complex concepts without ambiguity. At its core, physics seeks to uncover universal laws that govern nature. These laws must be expressed in a form that is exact and consistent, and mathematics provides that form. However, mathematical power alone is not enough. Without clarity, equations can become opaque, misleading, or even contradictory. History shows that progress in physics often depends not on discovering new equations, but on understanding existing ones more clearly. Mathematical clarity ensures that a theory means exactly what physicists think it means, no more and no less. One of the greatest challenges in modern physics is that its subjects are abstract. Quantum mechanics describes probabilities rather than certainties, and relativity replaces absolute space and time with flexible geometries. These ideas are deeply counterintuitive. Mathematics allows physicists to work consistently within these strange frameworks, but only if the mathematical structure is clearly defined. Vague or poorly understood mathematics can lead to false conclusions, apparent paradoxes, or endless debates that stall progress. Mathematical clarity is also essential for distinguishing physical reality from mathematical artifacts. In many advanced theories, calculations can produce infinities, ambiguities, or multiple possible solutions. Without clear mathematical reasoning, it becomes impossible to know which results are physically meaningful and which are simply consequences of the chosen method. Clear mathematics helps physicists identify assumptions, track approximations, and understand the limits of a theory's validity. Another critical role of mathematical clarity is reproducibility. Science advances through shared understanding. When a physicist presents a result, others must be able to follow the reasoning, repeat the calculations, and verify the conclusions independently. If the mathematics is unclear or overly obscure, this process breaks down. Clear mathematical presentation allows ideas to spread, be tested, corrected, and improved. In this sense, clarity is not just a personal virtue, but a communal necessity in scientific progress. Modern physics is also highly collaborative and international. Researchers from different backgrounds, cultures, and training traditions work together. Mathematics serves as a universal language, but only when it is used precisely. Clear definitions, consistent notation, and transparent derivations ensure that physicists can communicate across specialties. A lack of clarity can create artificial divisions, where scientists argue not because they disagree about nature, but because they interpret the mathematics differently. The development of quantum field theory offers a powerful example of why mathematical clarity matters. Early versions of the theory were extraordinarily successful in predicting experimental results, yet they were plagued by conceptual confusion. Calculations often led to infinite quantities, and different mathematical approaches seemed incompatible. It was only through careful clarification of the mathematical structure that physicists learned how to interpret these infinities and extract meaningful predictions. Once the theory was organized clearly, it became one of the most precise frameworks ever created. Mathematical clarity also plays a crucial role in identifying deep connections between different areas of physics. Often, theories that appear unrelated on the surface turn out to share the same underlying mathematical structure. Recognizing these connections can lead to unification, simplification, and new insights. Without clear mathematics, such connections remain hidden. With it, physicists can see patterns that suggest broader principles governing nature. In modern theoretical physics, clarity is especially important because experiments are often extremely expensive or technically difficult. In fields such as particle physics or cosmology, experimental tests may take decades to design and complete. During that time, theory must guide experiment. Clear mathematics helps physicists determine which predictions are robust and which depend on uncertain assumptions. This prevents wasted effort and helps focus experimental searches on the most promising directions. Clarity also protects physics from becoming detached from reality. Complex mathematics can sometimes give the illusion of progress, even when physical understanding is weak. Clear mathematical reasoning forces physicists to confront what their equations actually imply and whether those implications make sense in the physical world. It encourages humility and rigor, reminding scientists that elegance alone is not evidence of truth. Education is another area where mathematical clarity is vital. Modern physics is already challenging for students, and unclear mathematical presentation can make it unnecessarily inaccessible. When concepts are expressed with clarity, students can build genuine understanding rather than relying on memorization. This is essential for training the next generation of physicists, who must not only use existing theories but extend them into new territory. Finally, mathematical clarity supports the philosophical integrity of physics. Physics is not just about calculating numbers. It is about understanding reality. Clear mathematics allows physicists to ask meaningful questions about what a theory says about space, time, matter, and causality. It helps separate interpretive issues from technical ones, enabling deeper reflection on the nature of the universe. In modern physics, where theories push the limits of imagination and observation, mathematical clarity is the foundation that holds everything together. It ensures precision, enables communication, reveals hidden connections, guides experiments, and preserves the link between theory and reality. Without it, even the most powerful equations risk becoming meaningless symbols. With it, mathematics becomes what it is meant to be in physics, a clear window into the fundamental workings of the universe. Dyson's influence, despite never earning a PhD, is one of the most striking examples in modern science of how intellectual impact does not depend on formal credentials, but on insight, clarity, and originality. In a world where academic titles often define authority, Freeman Dyson stands out as a figure whose ideas reshaped physics without following the conventional academic path. His career challenges common assumptions about how scientific excellence is measured and demonstrates that deep understanding and creative synthesis can matter more than degrees. Freeman Dyson entered physics during a period of extraordinary transformation. Quantum mechanics and relativity had already overturned classical ideas, and physicists were struggling to build consistent theories that could explain the subatomic world. Dyson studied mathematics and physics at Cambridge and later moved to the United States, where he worked alongside some of the greatest minds of the 20th century. Yet, unlike most of his peers, he never completed a doctoral dissertation. This fact did not reflect a lack of ability or ambition, but rather his unconventional approach to learning and discovery. What made Dyson exceptional was his ability to see connections others missed. While many physicists focused narrowly on solving specific technical problems, Dyson excelled at understanding the structure of theories as a whole. He had a rare talent for translating between different mathematical languages and conceptual frameworks. This skill allowed him to make contributions that were foundational rather than incremental. His work often clarified and unified ideas developed by others, amplifying their impact and making them accessible to the broader scientific community. Dyson's most famous influence came from his work on quantum electrodynamics, where he demonstrated the equivalence of different formulations developed by other physicists. At the time, these formulations appeared so different that many believed they represented competing theories. Dyson showed that they were mathematically consistent with one another and described the same physical reality. This insight did not require inventing a new theory, but it demanded deep understanding and intellectual courage. It was precisely the kind of contribution that traditional academic structures sometimes undervalue, yet it proved essential for the progress of physics. Despite lacking a PhD, Dyson quickly earned the respect of leading scientists. Figures such as Richard Feynman and Julian Schwinger recognized the importance of his work and treated him as an equal. This respect was not granted lightly in an era when formal credentials were highly prized. Dyson's acceptance among elite physicists shows that in science, credibility ultimately comes from the strength of one's ideas and the clarity of one's reasoning. Dyson's career also highlights the importance of independence in scientific thinking. Without the pressure to conform to a specific academic lineage or research program, he was free to explore ideas across disciplines. He moved comfortably between physics, mathematics, astronomy, and even philosophy and public policy. This intellectual freedom allowed him to ask broader questions about science and its role in society, further extending his influence beyond technical research. Another reason Dyson's lack of a PhD did not limit him was his extraordinary communication skills. He was not only a brilliant thinker, but also a gifted writer and speaker. Dyson had the ability to explain complex ideas with elegance and precision, making them understandable without oversimplifying them. This skill amplified his impact, as it allowed his ideas to shape how others thought about physics. In science, the ability to communicate clearly can be as important as the ability to calculate, and Dyson mastered both. Dyson's influence also challenges the idea that scientific progress is driven only by specialization. Modern physics often rewards narrow expertise, yet Dyson's strength lay in synthesis. He brought coherence to complex theories and helped create shared frameworks that others could build upon. This role is essential, but sometimes invisible, as it does not always result in a single, easily labeled discovery. Dyson's career shows that science needs thinkers who can organize, interpret, and connect ideas, just as much as it needs those who generate new ones. His example also carries an important message for young scientists. Dyson demonstrated that curiosity, rigor, and creativity matter more than rigid career paths. While formal education is valuable and often necessary, it is not the sole measure of scientific worth. Dyson's life suggests that true learning is a continuous process driven by passion and discipline rather than credentials alone. Beyond physics, Dyson's influence extended into public discussions about technology, ethics, and the future of humanity. He wrote extensively on topics ranging from space exploration to environmental responsibility, bringing scientific insight into broader cultural conversations. His authority in these discussions did not come from academic titles, but from a lifetime of thoughtful engagement with ideas. This further illustrates how intellectual influence can transcend institutional boundaries. Dyson's story does not diminish the value of formal education, but it reminds us that science is ultimately a human endeavor. Creativity, insight, and understanding cannot be reduced to certificates or degrees. His career stands as evidence that the progress of knowledge depends on diversity of thought and freedom of inquiry. By contributing profoundly to physics without ever earning a PhD, Freeman Dyson reshaped not only quantum field theory, but also our understanding of what it means to be a scientist. In the end, Dyson's influence, despite never earning a PhD, reinforces a timeless truth about science. Ideas matter more than titles. His legacy is a testament to the power of clarity, synthesis, and independent thinking, proving that the deepest contributions often come from those who see beyond conventional boundaries and dare to understand the whole rather than just the parts. Freeman Dyson's impact on particle physics and quantum field theory tools lies not in discovering a new particle or proposing a single famous equation, but in shaping the very methods physicists use to think, calculate, and communicate. His contributions transformed quantum field theory from a confusing and fragmented subject into a practical and reliable toolkit that could be used across particle physics. Because of Dyson's work, generations of physicists gained tools that made the invisible world of particles calculable, testable, and understandable. Before Dyson's influence, particle physics was entering a period of rapid experimental discovery, but theory struggled to keep up. Quantum field theory, which combines quantum mechanics with special relativity, was the natural framework for describing particles and their interactions. However, it was extremely difficult to use. Calculations often produced meaningless infinite results, and different theoretical approaches appeared incompatible. Physicists could predict experimental outcomes with remarkable accuracy, yet many did not fully understand why the theory worked. This lack of clarity threatened the foundations of particle physics. Dyson's first major impact was organizing quantum electrodynamics into a systematic computational framework. He clarified how interactions between particles could be calculated step by step using perturbation theory. Instead of viewing calculations as isolated tricks, Dyson showed how they followed from a consistent expansion of the underlying theory. This organization turned quantum field theory into a practical tool rather than a collection of ad hoc methods. One of Dyson's most lasting contributions to particle physics was his role in formalizing Feynman diagrams as standard tools. While Richard Feynman introduced these diagrams as intuitive pictures of particle interactions, many physicists initially viewed them with skepticism. Dyson demonstrated that each diagram corresponded precisely to a mathematical expression derived from quantum field theory. He showed how to systematically generate diagrams, interpret them, and compute their contributions to physical processes. This transformation had enormous consequences. Feynman diagrams allowed physicists to visualize interactions such as particle scattering, decay, and emission of radiation. More importantly, they provided a clear set of rules now known as Feynman rules that could be applied across different theories. These tools became central to particle physics, making complex calculations manageable and reproducible. Today, nearly every calculation in particle physics relies on methods Dyson helped legitimize and organize. Dyson also played a crucial role in clarifying renormalization, one of the most important tools in quantum field theory. Early calculations in particle physics produced infinite values for observable quantities like mass and charge. This was deeply troubling, as infinities have no physical meaning. Dyson showed how renormalization could be understood as a systematic process rather than a mathematical trick. He helped explain why only a limited number of parameters needed to be redefined, and how this procedure preserved the predictive power of the theory. By clarifying renormalization, Dyson strengthened the credibility of quantum field theory as a foundation for particle physics. This understanding later became essential for the development of more advanced theories, including those describing the weak and strong nuclear forces. Without a clear framework for handling infinities, modern particle physics would not exist in its current form. Another important aspect of Dyson's impact was his emphasis on mathematical structure and consistency. He helped physicists recognize which features of quantum field theory were essential and which were artifacts of specific calculation methods. This distinction allowed researchers to generalize techniques from quantum electrodynamics to other areas of particle physics. As new particles and forces were discovered, physicists could adapt existing tools rather than invent entirely new frameworks from scratch. Dyson's influence extended to the culture of theoretical physics. He encouraged clarity over excessive formalism and understanding over blind calculation. His work showed that powerful tools must be grounded in clear reasoning to be trusted and widely adopted. This attitude shaped how particle physicists approached new theories, emphasizing transparency and internal consistency. The tools Dyson helped establish became central to the development of the standard model of particle physics. Techniques such as perturbation theory, diagrammatic expansions, and renormalization were applied to describe electromagnetic, weak, and strong interactions within a unified framework. While Dyson did not create the standard model himself, his contributions made its construction possible by providing a stable mathematical and conceptual foundation. Dyson's impact is also visible in how particle physics is taught. Modern textbooks present quantum field theory as a coherent set of tools rather than a historical struggle filled with confusion. Students learn diagrammatic methods, renormalization techniques, and systematic expansions as standard practice. This educational clarity is part of Dyson's legacy, as it ensures that new generations of physicists can build on established methods without repeating earlier misunderstandings. Beyond specific techniques, Dyson influenced how physicists think about theory itself. He showed that progress often comes from synthesis and organization rather than constant invention. By refining and unifying existing tools, he enabled particle physicists to focus on deeper questions about the nature of matter and forces. His work reminds us that scientific advancement depends as much on understanding and communication as on discovery. In summary, Freeman Dyson's impact on particle physics and quantum field theory tools was profound and enduring. He helped transform abstract ideas into usable methods, clarified how calculations should be performed and interpreted, and established tools that became central to modern physics. Through his work, quantum field theory evolved into a reliable and flexible framework, empowering particle physics to achieve some of its greatest successes. Dyson's legacy lives on every time physicists draw a diagram, renormalize a theory, or calculate the behavior of particles at the smallest scales. Dyson's broader vision connecting science, philosophy, and society reflects a rare kind of scientific thinking, one that refuses to isolate technical knowledge from human values, ethical responsibility, and long-term imagination. Freeman Dyson believed that science was not just a professional activity carried out in laboratories and equations, but a deeply human enterprise that shapes how societies think about the future, meaning, and responsibility. His vision extended far beyond physics, linking scientific discovery to philosophical reflection and social consequences in a way few scientists have managed so consistently. At the heart of Dyson's world, was the idea that science is part of culture, not separate from it. He rejected the notion that scientists should remain silent about moral, social, or philosophical issues. For Dyson, scientific knowledge carried obligations. Discovering how the universe works also meant reflecting on how that knowledge affects humanity's choices. This perspective placed him in contrast with more narrowly focused scientists who preferred to limit their influence strictly to technical research. Dyson saw science as a source of wonder rather than domination. While many 20th century scientists emphasized control over nature through technology, industry, and power, Dyson emphasized understanding, coexistence, and creativity. He believed that science should expand human possibilities without destroying the natural and social systems that support life. This belief guided his thinking on issues such as environmental protection, nuclear technology, and space exploration. Philosophically, Dyson was deeply interested in the limits of scientific knowledge. He often spoke about what science can explain and what it cannot. While he strongly defended rational inquiry, he resisted the idea that science alone could answer all questions about existence, meaning, or value. He believed that philosophy, ethics, religion, and art all addressed aspects of human experience that science could illuminate but never fully replace. This balanced view helped bridge the often hostile divide between scientific and humanistic ways of thinking. Dyson also challenged scientific dogmatism. He was skeptical of claims that any single theory represented the final truth about nature. In his view, science advances through diversity of ideas, disagreement, and imagination. He argued that progress often comes from unexpected directions and unconventional thinkers. This belief aligned with his own career, which thrived on synthesis rather than rigid specialization. By promoting intellectual openness, Dyson encouraged a healthier scientific culture, one less focused on authority and more focused on curiosity. One of the most important ways Dyson connected science and society was through his writing. He believed that scientists had a responsibility to communicate clearly with the public. Rather than simplifying science into slogans, he aimed to share its complexity honestly while preserving its sense of wonder. His essays and books addressed non-specialists without talking down to them, inviting readers into the scientific conversation rather than excluding them. This approach helped build trust between science and society at a time when that trust was often fragile. Dyson was particularly concerned with the ethical implications of technology. Having lived through the atomic age, he understood how scientific breakthroughs could be used for both progress and destruction. He did not see technology as inherently good or evil, but as something shaped by human choices. This led him to advocate for thoughtful governance, moral reflection, and long-term thinking. He believed that society must guide technology with wisdom rather than fear or blind optimism. Environmental issues occupied an important place in Dyson's thinking. He acknowledged the seriousness of environmental challenges, but resisted simplistic narratives of doom. Dyson believed that human creativity and technological innovation could help address environmental problems if guided responsibly. His optimism was not naive. It was rooted in his belief that science, when aligned with ethical reflection and social cooperation, could expand rather than limit humanity's future. This perspective encouraged constructive engagement rather than despair. Dyson's vision of space exploration further illustrated his integration of science and philosophy. He viewed space not just as a scientific frontier, but as a canvas for human imagination and long-term survival. He argued that exploring and inhabiting space could deepen humanity's understanding of itself and its place in the universe. At the same time, he emphasized that such exploration must respect life and avoid repeating the destructive patterns of Earth's history. For Dyson, space was not an escape from responsibility, but an extension of it. Another key aspect of Dyson's broader vision was his respect for uncertainty. He believed that uncertainty was not a weakness of science, but one of its greatest strengths. By acknowledging what we do not know, science remains flexible, creative, and open to revision. This attitude had philosophical significance, as it encouraged humility in both individuals and institutions. Dyson warned against scientific arrogance, arguing that overconfidence could lead to poor decisions with serious social consequences. Dyson also emphasized the importance of intergenerational thinking. He often spoke about humanity's responsibility to future generations, especially when making decisions involving long-term risks. Whether discussing environmental change, nuclear technology, or space exploration, he urged society to think beyond short-term gains. This ethical stance connected science directly to questions of justice, responsibility, and care for those not yet born. In connecting science, philosophy, and society, Dyson embodied a holistic model of intellectual life. He showed that a scientist does not have to choose between technical rigor and moral reflection. Instead, he demonstrated that the deepest understanding of the universe emerges when scientific insight is combined with philosophical humility and social awareness. His work reminds us that science shapes the world not only through equations and experiments, but through the values and visions of those who practice it. Dyson's broader vision remains deeply relevant today. In an age of rapid technological change, global challenges, and ethical uncertainty, his approach offers a guiding principle: knowledge must be accompanied by wisdom. By linking science to philosophy and society, Freeman Dyson left behind not just a scientific legacy, but a model of responsible and imaginative thinking about humanity's future. His lasting legacy on how physicists think and communicate ideas is one of Freeman Dyson's most profound contributions to science. While many physicists are remembered for specific discoveries or equations, Dyson is remembered for changing the intellectual habits of physics itself. He reshaped how physicists organize thoughts, share insights, and build understanding across different schools of thought. This legacy continues to influence the culture of physics long after his most technical work was completed. At a fundamental level, Dyson transformed how physicists think about theories. Before his influence, Physics was often divided into competing formalisms, each with its own language and methods. Physicists frequently argued over which approach was correct, even when they were studying the same phenomena. Dyson showed that such divisions were often superficial. By revealing deep equivalences between different formulations, he taught physicists to look beyond appearances and search for underlying unity. This habit of seeking structural connections became a defining feature of modern theoretical physics. Dyson's approach encouraged physicists to value understanding over allegiance to a particular method. He demonstrated that different mathematical languages can describe the same physical reality, and that no single formalism has a monopoly on truth. This insight changed how physicists evaluate new ideas. Instead of asking whether a theory fits a preferred style, physicists learned to ask whether it is internally consistent, physically meaningful, and connected to other frameworks. This shift reduced unnecessary rivalry and fostered collaboration. Another key aspect of Dyson's legacy is his emphasis on clarity in communication. He believed that ideas are not truly understood until they can be explained clearly. In his own work, Dyson carefully organized complex theories into transparent structures, making them accessible without sacrificing rigor. This set a powerful example. Physicists increasingly recognized that clear presentation is not a luxury but a responsibility. Today, well-structured arguments, consistent notation, and explicit assumptions are expected standards in theoretical work, reflecting Dyson's influence. Dyson also changed how physicists communicate across generations. By helping to standardize tools and methods, he made advanced theories teachable. Quantum field theory, once considered nearly incomprehensible, became a subject that could be systematically learned. This transformation shaped education in physics. Students were no longer expected to navigate a maze of conflicting approaches. Instead, they were introduced to a unified framework. This pedagogical clarity allowed new generations to contribute more quickly and confidently to research. In addition, Dyson's work encouraged physicists to embrace visual and intuitive thinking alongside formal mathematics. By legitimizing diagrammatic methods as precise tools, he showed that intuition and rigor are not opposites but partners. This changed how physicists think about problem solving. Visual representations, conceptual models, and physical interpretation became recognized as valuable components of serious theoretical work. This balanced approach remains central to how physicists develop and communicate ideas today. Dyson's legacy also includes a cultural shift toward intellectual humility. By showing that multiple approaches can coexist and be equivalent, he weakened the tendency to treat any single method as final or absolute. Physicists learned to be more open to alternative perspectives and more willing to revise their understanding. This humility is essential in a field where theories are constantly tested and refined. Dyson's example reminded physicists that confidence should come from understanding, not authority. Another enduring influence is Dyson's role as a translator between communities. He demonstrated that progress often depends on individuals who can move between different subfields, languages, and styles of thinking. This role is now widely recognized as essential in large scientific collaborations. Physicists value those who can connect ideas, synthesize results, and communicate across boundaries. Dyson helped legitimize this integrative role, which had previously been undervalued compared to narrow specialization. Dyson also shaped how physicists communicate with the broader world. He believed that scientists should engage openly with society and explain their work honestly. His writing style, clear, reflective, and respectful of the reader, set a standard for scientific communication beyond academic journals. Many physicists today see public communication not as a distraction, but as a meaningful extension of their work. This broader engagement helps build trust between science and society, a need that remains critical. His influence extends to how physicists evaluate success and contribution. Dyson's career showed that impact is not limited to single discoveries or formal titles. By organizing, clarifying, and unifying ideas, he demonstrated a different model of scientific excellence. This expanded view has encouraged the physics community to value synthesis, mentorship, and communication as integral parts of progress. Finally, Dyson's legacy lies in the mindset he inspired. He encouraged physicists to be curious, open-minded, and reflective. He showed that science advances not only through technical brilliance, but through the ability to listen, translate, and connect. His approach fostered a culture where ideas are shared, debated, and refined collectively rather than guarded or imposed. In sum, Freeman Dyson's lasting legacy on how physicists think and communicate ideas is woven into the fabric of modern physics. He taught physicists to seek unity beneath diversity, to value clarity and communication, and to respect multiple ways of understanding nature. His influence shaped not just what physicists know, but how they think, talk, and collaborate. Through this enduring cultural transformation, Dyson continues to shape physics as a living, human enterprise.